Welcome back to my course Aspects of Biochemical Engineering. Now, in the last lecture, I tried to discuss the industrial fermentation process and the material analysis. Now, when we discuss the industrial fermentation process, we have come across the several things. We have come across the bioreactor. Bioreactor is the vital things because where the biochemical reaction take place, and I told you that main issue is that how to maintain the sterility of that particular process, so that our desired organism can grow in that particular environment and to get the desired amount of product. And for doing so, I have already shown you in the last lecture that different type of the controllers are used. Now, in this lecture, we are going to discuss the process control of the biochemical processes, that what are the different process control that we use in the biochemical process. As you know, the chemical and biochemical industry, both the different type of process control is required to give the optimum environment so that we can maximize the product formation. So, this particular lecture its main purpose is to give you the detailed information, what are the different control system we use, how it function, and all this information I try to share with you. Now, first let me tell you that process control parameters that involve in this bioprocess, they maintain the optimum conditions for product formation in the complex environment. In a bioreactor required the control and measurement of at least the few parameters that I told you. Suppose we know that your organism, they are very sensitive to temperature, the environment, the temperature, pH, dissolved oxygen, that plays very important role. Am I right? If it is the aerobic fermentation process, so that you have to maintain. So, to maintain that, what are the different control systems required? Almost all fermenters having the pH, temperature, dissolved oxygen control. The maintenance of the sterility in a fermenter impose a severe limitations on obtaining online measurement of the fermentation parameters. So, whenever we draw the sample, whenever do anything in the system, we always consider the sterility of the process, how we can draw the sample. Also, I can give a typical example. Suppose this is a fermenter, and this is suppose this is you are drawing the sample. So, what we basically do, we have here, suppose here we have ball valve, and here there is the live steam line, live steam line. The first we pass the steam in this pipeline just to ensure the line is 100% sterilized. Then we draw the we open this ball valve and take it in the test tube, and then close it, and again we pass the steam, so that just to make the ensure that pipeline is sterilized. So, that sterility part we try to maintain in this particular fermentation process. The process control strategy of bioprocess are very primitive in comparison to the chemical industry due to lack of online sensor and reliable models. So, this is another problem that we have. Now, let us see that what are the different operational parameters that we have in the bioprocess. Now, we can divide it into three different categories. So, one is called physical parameter, another called chemical parameter, another is the biological parameter. Am I right? Now, physical parameter means what? The first parameter that come in picture, that is the temperature, and second parameter is the bioreactor pressure, because what pressure is maintained, because usually our biological system operated close to 1 atmospheric pressure. Agitation speed, we cannot increase the agitation speed too high, because if we mostly use the mechanical agitator. If we increase the agitation speed, it gives some kind of searing effect, and if there is searing effect, that will hamper the growth of the microorganism. Then gas flow rate, because what we call air flow rate, that we important. The total volume, that is very important. Then total volume we also monitor. that how we maintain monitor the total volume. We can monitor either by using watch glass or by using some kind of sensing device nowadays available, that from that we can find it out. The feeding rate, we can find out that power input we can calculate, and the foam, that is the things, that is the parameters we have in this fermentation system. Then other things is the reactor weight, the feeding tank weight, the culture viscosity, gas holding up, and the gas mixing pattern. So these are this undergo in the physical techniques. And chemical, we have pH and dissolved oxygen, and another things we have dissolved carbon dioxide, redox potential, we have out gas analysis, substrate, product, enzyme activity, volatile compounds, conductivity, biomass composition, metabolites profile, and the mineral ions. So different parameters we can estimate in the bioprocess. And biological, we have cell morphology, cell viability, optical density, cell dry weight, and cellular composition, specific growth rate, specific substrate consumption rate, and the specific product formation rate. Then we have oxygen uptake rate, carbon dioxide production rate, respiratory quotient. Then we have growth inhibitor, protein, DNA, RNA, ATP, and AMP. That these are the different parameters we can maybe use for the operating the different bioprocesses. Now let us see that how we monitor the physical parameters, like that temperature. Let's say, for example, that is we use the resistance thermometer or thermistor, because I told you it is basically the bimetallic. Am I right? Now we know the expansion characteristics of the metal, that depends on, it varies on depends on the conductivity. Am I right? So depending on this conductivity of the metals, the expansion and contraction that takes place, and from that we can monitor the temperature. This is what we call resistance thermometer. And but here we don't use the mercury thermometer. The pressure, we use the manometer. Manometer is very small technique that we have. We know this manometer, this we put the liquid, and suppose this is connected with your the reactor, that this is the reactor that we have, and then this pressure difference, that we will find out, from that we can calculate what is the pressure inside the reactor, that we can calculate. Then agitator shaft power, this is wattmeter, that we can or strain gauge we can use. Agitator speed can be estimated by using tachometer, because in our day-to-day life we also use, we have seen that in our car and other things, we if we want to find out what is the speed of the wheel, that we can find out with the help of tachometer. Foam is the rubber sheet electrode that is used, and gas flow meter, we have already told rotameter is used, and rotameters we have a flow I will discuss in details, and liquid flow rate is the magnetic inductive flow. But here I want to point out, in the biochemical industry we use the peristaltic pump. Now what is peristaltic pump? Peristaltic pump is kind of that you have kind of that you have this rod is there, and here what you do, you put a pipe around this, and it rotates like this, and it follows the principle just like a stopper, that we have in a stopper. What you do, we press it to take the air out, and when they immerse in the water, with the release it, then with the vacuum the water will suck into the tube, that so this is like this. So when this shaft move, then it press this tube. This is mostly made of silicon tube. So that so when you press it takes the air out, and then the air this way, then it creates a partial vacuum here, so that if it is connected with some kind of water tank or liquid tank, the water will suck in. And why it used in this biochemical process? Because nothing is exposed to the atmosphere, everything remains inside the pipeline. So we can maintain the sterility very easily. Viscosity, maybe if we measure with the help of viscometer, we know the Brookfield viscometer is largely used. Turbidity is used by turbidometer, and turbidometer and colorimeter is a little bit different. That turbidometer is the OD we determine on the basis of that scattering of the light particles. Like suppose the particles there, that your light will be scattered like this, and that when you have detector here, this is the light source we have here, then we find out how much of light is penetrating this. From that we can find out what is the density of the cell present in the sample. Now this is how the resistance thermometer looks. This is the sensing elements, and this is the lead support sheath and mounting thread and connecting lead. They are also called the resistance temperature detector, which are used to measure the temperature. They operate on the measurement of principle that materials element resistance changes with temperature. As I pointed out, the resistance changes with respect to temperature that we measured. They consisted of length of fine wire wrap around the ceramic and glass core, and RDT wire comprises of pure material, typically platinum, nickel and copper. RDT are fragile, and they are often housed in a protective probes. So this is RDT means resistant temperature detector. Next is the foam control. Next is the foam control, which is a common feature of any biochemical industry, foam formation. And why it is very much required? Because you see that in the fermenter, suppose this is the fermenter, and if you have foam formation, and I told you that here you have mechanical seal. Now if you allow the foam to build up, it will enter the mechanical seal and rupture the mechanical seal. And if you rupture the mechanical seal, then all air will enter into the system and spoil the system. So foam control is the anti-foam sensor are used to control the foam in the fermenter. Anti-foam system is foam contact in the rubber sheath, electrode, and electric circuit actuated solenoid valve to allow the passage of sterile anti-foam agent into the reactor. So there is a what is solenoid valve? Solenoid valve is a electrically controlled valve. So if as soon as that this sensor senses, then it goes to the here sensing is there. So it will immediately that it will open this solenoid valve and put the anti-foam oil into the reactor, and when it puts in the reactor, this foam will be subside, and if a foam is subside, then it will not affect your mechanical seal at all. A deflection tuff is provided to ensure the uniform distribution of the anti-foam agent. The effect of anti-foam agent is supplemented by centrifugal effect of the foam breaker. The amount of anti-foam entering the fermenter is usually controlled by a timer in the circuit to the solenoid valve. Example of the anti-foam agent includes the castor oil, fatty acid, alcohol ester, paraffin oil, and silicone oil, vegetable or animal wax, etc. I can tell you that in our day-to-day life, if you look in the kitchen, that when we cook anything, that we particularly cook pulses, we find lot of foam formation is there, and we heat the pulses in the water, and to subside the foam we add some kind of oil. So, similarly in the fermentation industry we use different type of oil, maybe vegetable oil, maybe castor oil, we have paraffin oil, silicon oil, vegetable oil, but you know that the type of oil we use is varies from the industry to industry. Now, rotameter, because rotameter is kind of float, you know, that you can see here that this is the float, this is gravity float. So, when you pass, suppose you are passing your air through this, so it make a pressure. So, rotameter is the most widely used variable area of flow meter. The tapered glass tube with smallest diameter at the bottom. Tube contains the freely moving float, the rest on a top of at the base of the tube, and when the fluid is flowing, float rises until its weight is balanced, and by the upthrust of the fluid, the float reaches a position equilibrium, and its position then indicated in the rate of flow. The the flow rate can be read and adjusted in the scale, which is often is in a glass tube. The main advantage of the rotameter is that suppose you increase the air velocity, then flow rate is increases, then your float will rise, and this is the linear scale. Am I right? So, you can easily monitor that at different flow rate that what. So, you can control your flow rate very easily. That is why the rotameter is used in the fermentation industry for controlling the flow of the fluid. Now, we are talking about the equilibrium state. The force balance on a bob is written in the following expression: Fd plus Fb equal to W. What is Fd? Is the drag force, Fb is the buoyance force of the float, and W is the weight of the float. So, you know that this should be equal to this under equilibrium condition, this should be equal to this, and by definition all form of force term can be expressed in the following form: the Fd equal to Cd AB into rho f um squared by 2. Fd can be expressed like this, and W is the the weight. So, this is how we can find it out. The rotational viscometer, which is used for the viscosity of the fluid, particularly we know that Brookfield viscometer that is used for the measuring the viscosity of the fluid, that determination of the viscosity of the fermentation broth. Rotational viscometer made up of two parts, one that rotates, another that remains stationary. Usually the motor drive the measuring bob and the sample cup stand still. The torque required for turning the measured bob against the fluid, the viscous force is measured. The viscosity is proportional to the motor torque. Online measurement is difficult. Now, another thing is the turbidity meter. I try to explain the turbidity meter because this is, we know that principles of colorimeter. What is the principle of colorimeter? Suppose this is a light source, and we keep a solution here, and we pass a particular wavelength of light, and we measure the intensity of light here. You know, am I right? This is the detector, and this is the light source. A particular wavelength, or we find out, through scanning we find out that what wavelength you have maximum absorption, and that wavelength we do that in case of colorimeter. But in case of turbidometer, what we do, this is that. So, in case of colorimeter, it is due to absorption, light absorption. Now, here is not absorption, the part is the organism is this particle. So, you know, light is scattered, you know, it will strike here, it will strike here like this. If the density is more, that, you know, less light will penetrate through this tube. So, your light density measurement here will be less. So, here the term turbidity is used to describe the cloudy or milky appearance of the liquid or solid media. This turbidity is caused due to suspension of particles like sludge, limestone, yeast or microorganism. It is based on scattering or absorption of light by the suspended particles. The transmitted intensity can be determined by the Beer-Lambert equation, and that IT equal to I0 into 10 to the power minus k into Sc, where k is the molar turbidity coefficient of the solution. This measured intensity of transmitted light is a function of the concentration of the dispersed phase. So, this is how we measured the how much light has been emitted, that that we measured by this turbidity. This indicates the concentration of cells present in the particular media. Then question comes, these are all physical parameters. Then let us come to the chemical parameter. We have pH. I told you the pH probe is used and for pH monitoring. Now, whenever we use any kind of pH probe, first we shall have to calibrate. Calibrate with the standard buffer, with the standard buffer. We calibrate that, then we put the sample and we find it out. The redox potential also measured the kind of oxidation reduction potential of the liquid. Dissolved oxygen probe we measured with the help of dissolved oxygen DO probe. The dissolved oxygen, dissolved carbon dioxide by carbon dioxide probe. Exit gas analysis can be done by paramagnetic analysis of plate ionization detector and mass spectrometer. And liquid stream measurement by HPLC, mass spectrometer and enzymatic biosensor that is used for liquid stream measurement. Suppose I want to measure the how much glucose is there, we use some kind of glucose sensor just to find out how much glucose is there in the outgoing liquid. Now, pH probe, take the instance, the pH is a logarithmic measurement of the number of moles of hydrogen ion per liter. So, pH how we can write? pH equal to minus log into hydrogen ion concentration. Am I right? So, this is what is written there. The pH probe is measured the pH by measuring the voltage or potential difference of the solution in which it is dipped. So, for whatever that this kind of device we have either mostly we use the potentiometric. The potentiometric means voltage difference is comprised of two electrode. One is glass electrode, which is silver alloy electrical wire submerged in a neutral solution of potassium chloride, all content inside the thin bulb and made from a special glass containing salts metal such as the sodium or calcium. Reference electrode, which also a silver alloy electrical wire suspended in a solution of potassium chloride contained inside the same special glass bulb. So, this is how this pH probe looks, and this is how it is there, that this is the filling solution, this is the electrolyte that we have, and you can see this is the electrolyte, that this is the plastic tubes and this is the electrolyte solution, saturated KCl solution, and here you have the silver wire coated with AgCl, and this is the electrode, two electrodes we have, and this is the porous glass, and this is when you touch the liquid, then you sense here and measure the pH of the solution, and this reaction is like this, that H2O is the hydrogen ion plus OH ion in the aqueous solution. Now, pH probe, how you can calculate this potential? We can the E that potential difference equal to E cell equal to E0 minus RT divided by NF ln Ke. K is the equilibrium constant. Am I right? If you know the equilibrium constant of that particular that ion conversion process, this is called Nernst equation. On the basis of we can find out what is the voltage that we have. This is how pH probe is function. Now, dissolved oxygen probe, it looks like this. This is the membrane, this is the cathode which is made of gold, and the anode, this is made of silver, and this is the electrolyte that we have. And we measured on the basis of amperometrically we measured it. So, your pH we measure on the basis of potentiometric, and this we measured on the basis of amperometric. Amperometric means with the help of microammeter. Now, the above phenomena, if you look at, can be measured by current to voltage diagram. This is like this. This is negative balance. We can have this kind of structure, that correlation we have. The negative voltage applied to the cathode is increased, the current increases initially, but soon it becomes saturated. When the negative bias voltage is further increased, the current output of the electron increases rapidly due to the other reactions mainly. Now, one thing I want to tell here, how we calibrate this dissolved oxygen probe. First, in the fermenter, suppose this is the DO probe, first we spurge nitrogen, and just to drive all the oxygen out, and when your monitor shows that your result is constant, that we adjust to 0, and then this is replaced by air, and you will find the dissolved oxygen concentration increases, and when the number is constant, then that we fix as 100. So, your scale runs in between 0 to 100, and 100 stands for the saturated dissolved oxygen concentration. Suppose the reading is 90, 90 means 90%. 90% means if you 0.9 into saturated dissolved oxygen concentration, DO, that is saturation, that concentration. So, if we have any kind of chemical logbook, we will find the table where we will find at different temperature what is the saturated DO concentration. So, if you know that, if you know your temperature of operation, if you know the dissolved oxygen concentration, so you can easily find out what is the DO concentration. This is how it monitored. This is how it is done. I am not going in details. Similarly, we can find out the carbon dioxide probe, that how you can monitor. This is the infrared lamp detected the wave of light through the tube and filled with air, and IR light detector is used, which is measured the amount of IR light, thus heat is. So, this is like this, IR lamp is there, and you find out where gas in and gas out, and this is the detector. From the detector we can find out what is the concentration that we have. Now, this is the oxidation reduction potential that we have, which is measured by the tendency of the chemical substance to oxidize or reduce to another chemical substances. Sometimes it is very much required in case of fermentation process. The consists of OPR electrode and the reference electrode similar to the pH probe. So, pH probe and this sometimes we have both the pH probe clubbed with this with the oxygen reduction potential, but both the thing oxidation reduction potential and pH probe from the same probe, sometime we estimated. The same principles more or less we use here. Now, this is the automated process control system that we have that is used in the fermentation industry. Now, if you look at the scheduling, supervision and automation control in modern bioprocessing is done by advanced process control system, where all functions are implemented in software. Now, I want to tell here that that most of the industry, they have pneumatic control system. Pneumatic control means special regulating system. So, we can have a control modules that from that we can have all the information that we have, that as for example, this is the production tank we have, am I right? And this is the storage and processor. This is the seed tank that we have. This is storage and processor. This again, this is the seed tank, and this is the inoculation preparation. This is the compression filter. This is substrate preparation. This is the energy supply. This is the cell separation and disruption. This is the product separation, product processing, waste processing. So, these are the different units we have. So, we have different control units we have. So, we require all the control system for the different phases we use that. The main purpose of bioprocess control attributes the handling of offline analysis. Offline means we take the material out, then analyze, and receipt and scheduling and parameter estimation. the simulation and prediction and optimization. So, we monitor from outside, we take the sample. I can give the example of online that that we have two type of analytical system. We have online and offline. As for example, that suppose in a reactor, I can explain that like this. Suppose in a reactor, if we wanted to have some kind of online analysis, how we can do that? How we can do the online analysis? So, what we can have? We can have a pump here. So, here we can have some kind of this so you can have a bypass line here. So, you can connect it with like this. So, so here that I hope that it is not written properly. So, let me tell you, you draw the sample with the help of pump. It goes to the analyzer like this. Then this is a control environment. You pose some kind of chemicals. Then suppose you have colorimeter or spectrophotometer, or let us assume this is turbidometer, turbidity meter. Okay. So, we can easily find out that what is the cell density, and this information is connected with this pump, another pump here. That we set the pump in such a way, if the turbidity cross certain limit, then this pump will be on and take the material out from the system. This is how we can do the online monitoring system. Now, this we can do it offline. You can draw the sample out and analyze here. In the you have turbidometer, and in the turbidometer we can find out, and then on the basis of offline analysis you can take the material out. So, two type of analyzing device we have, one is online and another is offline. For the industrial development, the central objective of the computer control is to realize the economic interest in assuring the high operational stability, process reproducibility, and increased product yield together with maintaining the rigorous safety. So, this is the main purpose why we required this automatic control with the industrial purpose. We now most of the industry, they operated automatically because their manpower requirement in the process drastically reduced, because we have seen that when I discuss the batch process and continuous process, we have seen that in case of continuous process our productivity is more high, and not only that, the manpower requirement for the operation of the continuous process is 1/10 as compared to the batch process. So, this is how this control system plays very effective role in case of biochemical industry. So, in this particular lecture I give you the overall idea that what are the different control system we have. Mostly it can be divided into three different ways. One is physical, another is chemical and biological, and there are different parameters, because all parameters it is not possible to discuss in this lecture. That depending on your interest, you can do that. As for example, suppose you want to monitor the glucose concentration in the fermentation broth, we can use the glucose sensor, and you can find out when the glucose concentration cross after a certain limit, you take the material out. Or you can use some kind of product sensor. You can find out that how much product is formation is there. From that you can, when the product, I can give the example of that cell mass concentration can be estimated with the help of turbidity meter, and when your OD value reach up to a certain level, that then you ensure that your cell concentration reach to the desired level, then you take the material out. This is how we can operate the system, and we have different type of control unit. We have temperature control, we have pH control, we have DO control, we have that agitator speed control, we have antifoam oil we can control. The different type of control system we use to make the system operative and to make proper environmental condition and desired conditions, so that we can maximize our product formation. Thank you very much.